Hello, good people. Welcome to the next video. We're doing antiderivatives by using the method of partial fractions. We're doing partial fraction decomposition. And what that means is we're taking a fraction, a rational function like this, and we're breaking it up into little fractions that we're adding together. So the rule says that any fraction can be broken down into the sum of smaller fractions. How do I get the smaller fractions? I have to factor the denominator because each of the smaller factors has one of the factors in the denominator. So what we're going to do here as we look to solve the second example, we're going to need to factor this, and I'm going to do it here on the side. We're going to need to factor this denominator. Well, first of all, I notice they all have something in common. There's a greatest common factor, and that is x. And then I can see that I can factor this out even further into two binomials. And I believe that's going to be minus 4 and plus 1. And so this denominator, or rather this integrand, this rational function, this fraction, the denominator can be written as this. Because when I multiply these factors, I get back to x to the third minus 3x minus 4x. Great. I need that because if I'm going to break this big rational function fraction into little ones, then I need to say that this is the same thing as some number over the first factor plus another number over the second factor plus another number over the third factor. So as long as I have factored out my denominator, I can break it up into partial fractions, which is what we're doing here, and we can say that these two are equivalent expressions. But here's the deal. These are equivalent expressions for whatever x value I choose. So what we're going to do is we're going to multiply, and this is what we did in the previous video. We're going to multiply by the common denominator, which would be this product. So I'm multiplying this left side of the equal sign by x times x minus 4 times x plus 1. And I'm multiplying all of the right side, or maybe I should word it as each of the terms on the right side by x times x minus 4 times x plus 1. Why? Because when we do that, all of these will reduce out, and we're left with just the numerator. But on the other side, I have to individually multiply this times each of these fractions. So if I multiply the first one times that, the x's are going to reduce, and I'm going to be left with a times x minus 4 times x plus 1. Plus, if I multiply the second fraction times this product, I'm going to cancel the x minus 4's, and I'm left with b times x plus 1. And if I multiply the third partial fraction times that, I'll be left with c times x minus 4. All right, so now I'm left with this. Why do I now feel like this is more complicated than what I started with? Well, for now it is, but we're going to find the a value, the b value, and the c value in this equation. And the way we do that is we're going to choose an x value that is convenient for us. For example, if x equals 4, well then if x equals 4, we're going to have this on the left side of the equal sign. But when I substitute this 4 in here, I am going to, for x, I'm going to zero that out. So I'm substituting a 4 wherever I see a variable. What am I doing? I apologize. 4 plus 1, c times 4 times 4 minus 4. Because what's going to happen here? Well, anytime I have 4 minus 4, that's 0. And when I multiply it times everything else, that's going to go away. 4 minus 4 is 0. When I multiply that times everything else, that's going to go away. So really, I'm just left with whatever's here, which, by the way, would be 4 squared, which is 16, doubled, which is 32, and 32 minus 7, that would be 25, is equal to b times 4 times 5. Sorry, I was checking if I had written this incorrectly, but no, that is x plus 1, so that's 4 plus 1, and that's 5. So that means b is, if I multiply this, that'll be that. I'll divide by 20, and so 25/20ths is what b equals. It's also known as 5/4, by the way. Great, I got the value of b. But I can do that with another value. For example, I can do it with what if x equals 0? If x equals 0, well, then that's going to be 2 times 0 squared minus 7 equals. Now, I'm going to start substituting, but once I notice, if I substitute a 0 here, that's going to zero that out. That's gone. And if I substitute a 0 here, that's going to zero that out. That's gone. I'm not going to write it over here. And so everything's going to collapse down to this, which then becomes a times negative 4, and I forgot to put the 0 here, times 1. So really, this is just negative 4. And if I divide both sides by negative 4, I'm going to get my a value is 7/4. Great. But I could have also chosen, what if x equals, let me use the same color to keep it consistent. What if x equals negative 1? Well, if x equals negative 1, I'm going to substitute it into the left side. Now, think about it. If I substitute negative 1 in here, that's going to give me a 0. That's gone. And if I substitute negative 1 here, that's going to equal 0, and that's gone. So really, I'm just left with c times negative 1 times negative 1 minus 4. So if I do this calculation, negative 1 squared is positive 1 times 2. That's negative 5. If I subtract 7, and then on this side, that's 6 times, excuse me, negative 1 times negative 5. That's not 6. That's a c, senor. That's a c. Negative 1 times negative 5. That's positive 5. And if I divide both sides by positive 5, I'm going to get that c equals negative 1. All right. Why were we even doing that? Because if I know that I can decompose this into 3 partial fractions, I have now found the coefficients, the numerators of all of those. So that means here, and I'm going to try to zoom in as much as I can and still see everything. Here I can say that my a value is 7/4 over x plus my b value is 5/4 over x minus 4 plus my c value is negative 1 over x plus 1. And that is dx. Now I could break this up into separate integrals, right? Make sure that I have the dx, make sure that I have the dx. And then what's going to happen is I will be able to factor out each of those numerators. So I have 7/4 1 over x dx plus 5/4 1 over x minus 4 dx plus minus 1 1 over x plus 1 dx. Hey, the antiderivative of 1 over x, that's the natural log of x, or the natural log of the absolute value of x. Plus, here, I could use substitution where u is x minus 4. That means du is dx. And so this becomes 1 over u, which is going to be the natural log of u, the antiderivative. But you plug in the value of u back in, and it's going to produce, or it's going to end up being 5/4 natural log of the absolute value of x minus 4 minus, and I can do the same thing here. I can do a little u substitution where u is x plus 1. So du is dx. So therefore, I can replace this with a u and this with a du, and this would be natural log. So if you haven't noticed, it's pretty easy to apply this natural log antiderivative. What I usually tell students is, if the derivative of the denominator is in the numerator, I can use this natural log, right? Because if you remember, we had said that the antiderivative of 1 over u or I'm sorry, of this is the natural log of the absolute value of u. But if I write it like this, this is saying if the derivative of u is in the numerator and u is in the denominator, then the antiderivative is the natural log of u. Okay, well, the derivative of x is 1. Hey, that's in the numerator, so I can just do a natural log antiderivative. The derivative of x minus 4 is 1. Hey, that's in the numerator. I can do the natural log. And that's one of the reasons why we do partial fractions, is because when we create especially linear factors, it's a lot easier to take the antiderivative using the natural log shortcut. And so this is the antiderivative of what I started with. Is that a lot of work? That is a lot of work. I admit that is a lot of work. But I'm also showing like every step. And I'm also trying to explain things like step by step. So in due time, the more you practice these, the faster it's going to go. So I'm going to try to do one of these, and then in the subsequent video, maybe going at the pace a little bit faster, so that you can see kind of the process, the mechanics, and how we don't have to write everything down, and so on and so forth. Yes, I think this is a good place to pause here for this video, and we'll come back with another example.